Hey Christine, there's a couple of exponent rules that are really going to help you here. We use these rules anytime we have variables as bases or exponents. It allows us to keep solving the problem without really worrying about what the number is. So our first rule is called the product rule. And it states that if we have two exponents with the same bases, the base is the bottom number, and in this case the base is x. In all of these, it'll be x. What we do when we multiply two exponents with the same base, we basically just add the exponents. So x squared times x cubed, well, we can just add 2 plus 3 to get an exponent of 5. The second rule, called the quotient rule, that's the one that applies to you. In this example, we have x to the fourth divided by x to the negative 1. Now the rule states that when we're dividing two exponents with the same base, we subtract the exponents top minus bottom. So it's really like 4 minus 1, double negative there, so that's going to be x to the 5. And if I jump over to your problem, that's what was happening right here. Okay, you did the 360 divided by 5, that's 72. But now we have x to the 7 minus 3. So that's really x to the 10. That's where that comes from right there. Back to the rules, so we got a couple more. The next one is the power rule. Whenever we have an exponent that's raised to another exponent, we basically just multiply them. So 2 times 3 is 6. Now don't confuse the power rule with the product rule. A lot of people do that. The product rule, we add the exponents because we're multiplying two exponents with the same base. Here it's just an exponent raised to another exponent, so you got to multiply. Last couple of rules, anything to the 0 exponent is 1. Okay, it doesn't matter what the base is. X, Y, Z, 3, 10, doesn't matter. Anything to the 0 exponent is 1. And anytime we have a negative exponent, it's never really simplified. What we do is we take the inverse or the reciprocal of it, because remember, any number, even an exponent, can be thought of as a fraction over 1. So what I do, if I flip it, what happens is the sign on the exponent will change. And basically, we always want to have things as positive exponents. Technically, this is not simplified right here. Okay? So those are our rules. Popping back over here. One step that you kind of missed, and you weren't really off too far, but like it created a lot more work for you. 72. What we want to do is we want to factor out the biggest perfect square, and that's 36. Remember, our perfect squares are these numbers here. Any number that is squared. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. These are all our perfect squares. So when you see a number like 72, I'm thinking, oh yeah, 36 times 2 gives me 72. So I just write a big radical sign or square root sign, and I just write it right underneath. Okay? Also, any variable with an even exponent, so 2, 4, 6, 8, 10, for example, is a perfect square as well. And what happens, now we can evaluate the perfect square part. So the square root of 36 is 6, and the square root of x to the 10 is x to the 5. What happens here, when you're taking the square root of an even exponent, it basically cuts the exponent in half. So half of 10 is 5. And then we just express this as square root 2, that stays under there. Okay? Now in your example, there was actually more that you could have done in here. All right, you could have pulled out a bigger perfect square because you had a quite a large number in there. So that's kind of your tip right there. But we're always going to go for the biggest perfect square you can get out of that. Okay? And again, that with that little trick here. And the reason why, if we thought about x to the 10, I could write that down as x squared times x squared times x squared 5 times using this product rule, right? X squared times x squared times x squared, because they would all add up to be x to the 10, and then we basically square root each one of those. That's why we get x to the 5th right here. But anyway, bit of a geek out, but I hope that helps. If not, let me know.